Okay, so here you can see my work with the integral test. I'm not sure what's going on with my notes there. But I found the integral, I set this equal to a function, I integrated it, and then I used b, used the limit as b goes to infinity. I got negative 1 over b plus, because it's minus a negative 1 over 1, and I found the limit as b goes to infinity, that drives this till 0. So this equals 1. So what I've just found is that this is going to converge because it's integral converges. Okay. All right. So let's see if I have some room to do this one below. Okay. So on this one, I would let my function f of n or f of x be 1 over the square root of x. So that's x to the negative 1/2. So I'm going to take the integral and I'm going to check that out. And we're talking about the integral from 1 to infinity again. And so I would want to make this like some limit. Okay. Alright, so let's see. The integral of x to the negative 1/2 is going to be 2x to the 1/2, I believe. Yep. And then from b to 1 is going to be 2 times the square root of b minus 2 times the square root of 1. As b goes to infinity, it doesn't matter. This is a growing function. Doesn't matter that I'm subtracting 2. This is going to go towards infinity. So this diverges. Okay. So at this point, I'm going to hop ahead. These things, when you see n or x written as a power on just the bottom, we have a name for this specific type of series. It's called a p series. Okay. And what we just found out was when it was squared, it converged, and when it was a square root, it diverged. And the generalization of that is, first of all, we have 1 over n to the p. It converges if p is greater than 1. We found that with when it was 2. It diverges if p is less than or equal to 1. And in that case, remember, when it was a square root, a 1/2 power, we found that it diverged. Where p equals 1, this is called the harmonic series. This is a special series. When it's called, when the power is 1 over n. And so what ends up happening when it is equal to 1 is, interestingly, it still is diverging there. Okay? So there is a general form of a harmonic series, which, so in other words, as long as the power of n is 1, there can be a coefficient and a b, but you might see harmonic series come in this form. So if we're going forward then, does this series converge or diverge? Let's look at the power. The power is 1.04. P is greater than or equal to 1. P is greater than 1. So this series converges. This one, P, is pi. Looking up here, pi is greater than 1. This also is going to converge, since p is greater than 1. Okay, so there's just an example of the p series and what generalizations we can make from our previous statement. Okay, let's see what other examples I have here to work through. Let's take a break and let's do just another example of the integral test so we can see another example of how that works. Let's take a look and let's use the integral test. the sum of n equals 1 to infinity of 1 over n squared plus 1. And so we're going to use the integral test to do this. Okay. Now, according to what we were just talking about with p-series, this is a form of a p-series. Okay. So my prediction is from over here, this is still the general form. Well, this is of a harmonic series. My guess is that it's going to converge because the power of n is greater than 1. Or, yeah, greater than 1. So I'm going to apply the integral test, though. So I'm going to let this equal the function f of x is 1 over x squared plus 1. Hopefully you can identify that. So I'm going to then take the integral from 1 to infinity of 1 over x squared plus 1 dx. And I can write that as the limit as b goes to infinity of that integral. And of course, the integral of that is arctangent, so this is the limit as b goes to infinity of arctan of x. Thinking about the arctangent function, let's just remember the arctangent function is the inverse tangent function. It's got a vertical asymptote or horizontal at positive pi halves and negative pi halves. So the limit as the arctan goes to infinity is pi halves. So I evaluate this. This is arctan of b minus arctan of 1. As I said, this is the limit as b goes to infinity. So if I were, I can't put infinity in there, but if as it approaches infinity, the limit does become pi halves. And the arctangent of 1 is pi fourths. Pi halves minus pi fourths is pi fourths. So this is going to a value. Therefore, since we reached some kind of limit, this series converges because its integral converges. Okay, so that's a little bit about harmonic and p-series and the integral test.